Welcome back. In this video we are going to do example 4.2.2 where we are asked to find the absolute extrema of f of xy is 2x to the fourth plus y squared minus x squared minus 2y on the region D given below. Let's first of all take a look at region D and identify the boundary curves. So in red here we've got the y-axis, which is the curve x equals 0. In green, here we have the horizontal line, which is y is equal to 2. And in blue, the diagonal line from 0, 0 to 2, 2 is the line y equals x. Now, if we take a look at our function, f is a polynomial. Polynomials are continuous. And since f is continuous, the extreme value theorem applies. So we know that there is, in fact, an absolute minimum and an absolute maximum to be found on this closed, bounded region. We need to start by finding some critical points. So let's look in the interior. And in the interior, we're looking for places where either the gradient of f does not exist, f is a polynomial, so that's never, or places where the gradient of f equals 0. For that to occur, we need both partials to be 0. So f sub x at xy is 8 x cubed minus 2x, which we can factor. So if we bring out 2x, we are going to have 4 x squared minus 1, or 2x times 2x minus 1 times 2x plus 1. F sub y at xy is 2y minus 2, which can be factored as 2 times y minus 1. We need the gradient to be 0, so we need to let both of the partials be 0 at the same time. So 2x times 2x minus 1 times 2x plus 1 needs to be 0, and 2 times y minus 1 has to be 0. We get as possibilities that x is 0, x is minus 1/2, or 1/2. For each of these, we have only one possibility of y, and that is the point or the place where y is equal to 1. So these are critical points of f, but we need to find those that are in the interior. So if we take a look at the point 0, 1, 0, 1 is here on the boundary. So that is strictly speaking not an interior point. Minus 1/2, 1. Also not an interior point. 1/2, 1. So if we split this down the middle, that's about 1. That's about 2. So 1/2, 1 is there. That's interior. So let's call that point A, and we'll keep that point. Now we need to look on the boundary. And there are 3 boundaries to look at. Let's start with the boundary where x is 0. If we're looking at x equals 0, we can create a function of a single variable. We're going to let g of y be the function where we plug in 0. So f of 0, y. And if we're plugging in 0 for y, no, for x, we're going to get y squared minus 2y. We want critical points of the boundary curves. So we want places where g prime is equal to 0 or does not exist. G prime is 2y minus 2. So g prime of y is equal to 0 when y is equal to 1. That is giving us a point, a critical point on the boundary. That is 0, 1. You'll notice that's the same critical point that appeared here. So it wasn't on the interior. In the interior, it's on the boundary. So let's call that point B. We also need to look where G prime does not exist, and that also is a polynomial, so that is never. Next boundary, let's look where y is equal to 2. In a similar fashion, we're going to create a function of a single variable h of x, which is going to be f of x and 2. And if we plug in y is equal to 2, we're going to get y squared is 4, and 2 times y is 4. Those will cancel each other out, and so we'll have the function h of x is 2 x to the 4th minus x squared. H prime is 8 x cubed minus 2x, and h prime is equal to 0. Well, at exactly the same places that x was equal to 0 in the interior. So at x is equal to 0, minus 1/2, and 1. That means that we're looking at places where y is 2 and x is each of these values. So we've got potential critical points here of 0, 2, minus 1/2, 2, and 1, 2. Let's take a look at those on the graph. 0, 2. 0, 2 is here. That is indeed on the boundary, so let's call that point C. Minus 1/2, 2. Well, minus 1/2, 2 would be out here. That is not on the boundary. And the point 1, 2. 1, 2 is also on the boundary. Not 1, 2, 1/2, 2. 1/2, 2. So let's get rid of that little point and put 1/2, 2 in its place. So that should be right above point A. And we'll call that point, well, we won't call it D because the region is called D, so we'll call that E. Last boundary curve to look at is when y is equal to x. So we're going to create yet another function. Let's call this j of x, and it's going to be f of x and x. We'll set y equal to x, which will give us, so if y is equal to x, these two terms are going to cancel out, and so I'll have 2x to the 4th minus 2y, but y is x. So 2x to the 4th minus 2x. We want critical points of j as well. So j prime of x, which reminds me I should have looked at places where h prime of x did not exist, and that also is never. It's a polynomial. J prime, now going back to here, we've got 8x cubed minus 2. So we want places where j prime, let's do the DNE first of all so we don't forget it, and that is never. And so j prime of x equals 0 is when x cubed is 2 over 8 or 1 over 4, so x is the cube root of 1/4. Now it's on the line y is equal to x, and so the y coordinate of that point is also the cube root of 1/4. So let's call that point f. F, which is going to have coordinates cube root of 1/4 and cube root of 1/4. So that is, I don't know, somewhere there-ish, let's say. So f is on the boundary. The last thing that we have to do is also to collect our corners or vertices. So we've got 3 corners to our region. One of them has already shown up on the boundary. The other 2 are missing. So let's add G, which is the origin, and H, which is the point 2, 2. So we've got all of these candidate points to find out which is the local minimum and which is the local maximum. We have to plug them in, all of them, into the function. So I've prepared a little table of values here where I've done exactly that. I've taken all of our points A through H, skipping D because D was the name of the region. I've taken all of our candidates, I've plugged them into f of xy and found the function value at all of these points. The smallest value, in which case here we have the lowest negative, that is going to be this guy. So that is our absolute min. Our highest value is here, our absolute max. So we can write this little summary on D. F attains an absolute min of minus 9/8 at the point 1/2 and 1, and obtains an absolute max of 28 at the point 2, 2.